I am your science communicator for today's journey, and I'd like to invite you into the strangest turning point life has ever staged. The first arms race underwater at the dawn of the Cambrian, roughly 541 million years ago. When vision sharpened, muscles woke up, and shells clicked into place like the first locks on a new world. Picture a calm seafloor before this moment, soft mats of microbes, slow grazers leaving quilted tracks, bodies simple as curtains and tubes, a planet catching its breath after the long quiet of the Ediacaran. Then, almost overnight in geologic terms, evolution stepped on the accelerator. Eyes appeared with hundreds of facets, jaws and spines followed, and predators learned to chase while prey learned to hide, to harden, and to dig. That is the battle line we are going to walk together. I am recording from a museum prep lab where shale slabs from famous sites like the Burgess Shale in Canada, Changjiang in China, and Sirius Passet in Greenland rest like dark books on a shelf. Each slab carries a page of the story, the ghost print of a fin, the rungs of a gill, the shadow of an eye. Next to me, Maya, a volunteer fossil hunter who grew up far from any ocean, leans over a binocular microscope and whispers every time she finds a bristle. She once told me she started volunteering because she wanted proof that wonder can fit into ordinary schedules between night shifts and school pickups. On my other side sits Theo, a wildlife artist who paints living fish for field guides and now tries to imagine animals no one has seen alive. We trade questions. How would a lens made of calcite focus underwater? How many muscles would you need to steer a serrated mouth? What does fear look like in an ecosystem that had never known a chase? Our subject today is Anomalocaris and its competitors, but really it is bigger than any single creature. It is the feedback loop between eyes, speed, and armor. The term arms race can sound like a cliché, yet in the Cambrian it describes a real escalation. Once some animals could see well, even dimly, being a blur or a shadow became a matter of life and death. A compound eye detects motion as a flicker across many tiny lenses called ommatidia, and the more lenses you have, the finer the flicker. One Cambrian eye preserved as a fossil holds thousands of facets, meaning that even at dawn it could spot contrast and aim a strike. Predators that sense distance could plan, prey that sensed looming shadows could bolt. Speed suddenly mattered. So did direction. Fins lengthened, body segments coordinated, and nervous systems grew circuitry that could update a moving world many times per second. Meanwhile, prey met speed with materials, collagen stiffened bodies, and biominerals like calcium carbonate and calcium phosphate hardened edges into spines, plates, and shells. Trilobites built eyes out of calcite crystals and armored cheeks out of interlocking segments, a design at once elegant and resilient in shifting currents. Other creatures wrapped themselves in soft spikes or scale-like plates. Some took cover by burrowing down into the sediment, leaving the first deep, looping trace fossils we read as escape tunnels. If you are wondering what set the fuse, several ingredients were in the mix: oxygen levels that allowed high-powered movement, developmental toolkits that could rearrange segments and appendages with small genetic tweaks, and ecosystems crowded enough that encounters became frequent. None of this was a single spark. It was 1,000 small invitations to try something new, and when one innovation worked, it changed the rules for everyone else. Maya finds a wafer-thin outline of a radiodont, the group that includes Anomalocaris, and gasps because the eye stalks are there, to crescents like rising moons. Theo sketches the stalks and asks whether compound eyes mean color vision. I explain that color depends on photoreceptor pigments and that we cannot know the hues these animals saw. Yet we can infer sensitivity to contrast and movement because the geometry of the lens array matches what modern arthropods use to track motion. He smiles and paints water full of faint halos. The halos a hint that being seen and seeing were shaping the dance. As we lift another slab, I tell a story as old as fear and hunger. Early hunters likely started as opportunists, nibbling soft tissue on dead animals, then on dying ones, then on anything they could catch. Mouthparts that were good at scraping turned into grasping tools. Flexible flaps became fins, burrowing feet became paddles. Anomalocaris, whose name means odd shrimp, did not have the shrimp shell of cartoons. It was a soft-bodied swimmer with two spiny frontal appendages to grab prey, a radial mouth like a pineapple slice that could contract, and large lateral flaps to ripple through the water. Its body plan looks exotic, but the logic is familiar. Find, seize, process, repeat. The prey responded in kind, and what had been a seafloor of gentle browsers became a stadium of moves and counter-moves. If you have ever watched children learn to play tag, you have seen the pattern at human speed. The moment someone discovers a shortcut, everyone else discovers a defense. Evolution plays by similar math, except the score is written in survival. Theo sets down his brush and says that eyes feel like the real tipping point, and I nod, because eyes turn space into a map and time into a warning. With eyes, the ocean stopped being a neighborhood and became a dynamic field of predictions. To live was to measure, and to measure was to change. When we talk about the Cambrian, we often list the celebrities, so let's meet them in the order a hunt might reveal them. A ripple of sand, a pause, and a flat-eyed trilobite inches forward, its calcite lenses packed like tiny windows, its jointed legs tickling the seafloor as it tests the current. Nearby, a creature with 5 eyes called Opabinia raises a flexible proboscis tipped like a grabber claw, as if someone assembled a face from spare parts and still made it work. Wiwaxia glides like a shredder with soft plates and long blades, and Halkyria carries a male of little sclerets that anticipate later armors. Above them swoops a radiodont, its broad flaps beating a rhythm across the water, its eyes crowded with ommatidia, its frontal appendages opening and closing like a pair of folding ladders. In this world, the race is not only to be the fastest, but to notice first. The physics of vision matter. The ocean filters light quickly, scattering blue and stealing reds. So a compound that spreads its detectors over a dome can harvest fleeting contrast from many angles. That design lets a hunter detect the direction a shadow is moving and predict where it will be. Trilobites answer with hard edges and the option to roll into a ball. Burrowers answer by stirring oxygen into deeper sediments and disappearing into them. And every time a new trick pays off, it reshapes the map of what else is possible, because evolution builds with what is at hand. Our lab day spills into a field day. We hike to a quarry where workers split shale like pages. Maya, who last week was told her overtime might vanish, needs the walk and the silent rhythm of the hammer. She shows me a paper-thin molt from a trilobite, the empty suit left after growth. I tell her that molting is both opportunity and risk. You grow in leaps, but while your new shell hardens, you are soft enough to miss a shadow. She nods and says she knows the feeling of being between suits. Theo takes notes on the way armor constrains movement and how joints solve it, sketching hinges that trade flexibility for safety. He asks about bite forces. We know some by subtraction. Bite marks on trilobite carapaces show semicircles the size of a coin, and repair scars tell us the victim lived to crawl another day. The fossil record rarely gives us motion, yet under a microscope you can read decisions, the burrow that doubles back, the clutch of eggs tucked under plates, the scar that healed crooked. Anomalocaris enters are seen like a rumor that you cannot ignore. Early fossils were found as separate parts, a pineapple ring mouth here, a spiny appendage there, a body flap elsewhere, and for years scientists puzzled over how they fit. When the pieces were assembled, a portrait of a swift predator emerged, large for its time, eyes like lanterns, mouth able to contract in a circle and perhaps crack thin shells or peel soft tissue. People often ask whether it ruled the seas. The fair answer is that it dominated some places, some of the time, because evolution does not crown permanent monarchs. Every advantage opens a counter path, thicker plates, deeper burrows, deceptive outlines, even simple teamwork of small scavengers making the job harder for a single hunter. The point is not a ladder of progress, but a web of responses. Back in the lab, Lynn, a graduate student who models vision in ancient arthropods, runs a simulation on a screen. Her code uses the geometry of fossil eyes to estimate how fine a moving edge could be resolved at different distances. She shows that an eye with thousands of facets gains little in stillness, but gains a great deal once target and hunter are moving. That is why speed and vision locked arms. She smiles and admits the simulation kept failing until she added noise, because real water flickers and real animals jitter. The honesty of that fix is its own lesson. Reality is never as clean as the diagram. We gather around a specimen of a tiny animal with a brain layout that suggests early centralization, and we talk about what nervous systems have to do when eyes arrive. Compress torrents of data into simple rules like turn toward, flee from, rise, dive, phrase. Those rules sound simple until you have to rewrite them every generation. In a notebook, I jot the phrase eyes make time visible. Once a creature can anticipate, behavior blooms. Sea floors that once favored sleeping on the surface now reward tunneling. Waters that once let you drift now punish hesitations. The first arms race is not steel against steel, but information against injury. And information, when it works, leaves fossils of absence, fewer bodies in the open, more traces underground, shells that look overbuilt for a reason you can only guess until you sketch an attacker. That rhythm leaves no soundtrack in stone, but it lives in the designs we see. Broad flaps for efficient undulation, frills that double as respiratory surfaces, bodies thin enough to sip the boundary layer where fresh water meets sediment. When we imagine the Cambrian, we must resist thinking in monsters and marvels alone and learn to think in trade-offs, because every eye is costly to build and maintain. Every armor is heavy, and every sprint spends precious currency. Maya laughs that this makes ancient life sound like her budgeting app, and I answer that survival is always accounting with teeth. Absolutely. Before we close, I want to linger on what shells change beyond defense, because armor is chemistry written into bodies. When animals began locking calcium carbonate and calcium phosphate into plates and tubes, they tied ocean chemistry to evolution in a new way. They pulled dissolved minerals from seawater. They buried those minerals when they died, and they changed how carbon and oxygen cycled through the planet. Whenever we split rock and find a ridge of shell, we are watching the planet learn a new line in its own script. I tell Maya this while we pack up, and she laughs because she thought she signed up to find monsters, not biogeochemistry. She tucks the molted suit into a tray and says it feels like a souvenir from someone who outgrew a fear. Lynn sends us a file of her simulation with a note that says, "Remember the noise," and I add that note to my talk outline for a community center visit. In the evening, we wheel a cart into a room where elders who have never taken a geology class sit beside kids who cannot stop asking about monsters. I begin with a question: how do you move through a world that suddenly sees you? Hands go up. Someone says, find friends. Someone else says, learn the shadows of your own street. A grandmother says, I roll up my windows at dusk. We talk about trilobites that rolled into a ball, about worms that vanished into working burrows, about animals that lit up their foreworld with eyes. I hold up a replica of an Anomalocaris appendage and ask them to imagine the first time a prey animal felt its skin touched by a grasping tool built for speed. It is small scale, but suddenly the arms race stops being yesterday's headline and becomes a lesson about attention. We are not here to draw a straight line from then to now. We are here to practice seeing how feedback loops shape behavior. In the Cambrian, vision multiplied choices. Today, information does the same, and our armor rules, habits, codes must stay light enough to let us move and strong enough to keep us safe. This is not a moral smuggled into science. It is what the data whisper when you stare long enough. I drove speed. Speed invited armor. Armor demanded better strategy. Strategy favored better sensors. And around the circle, the dance continued, sometimes ending in a stalemate we call stability, sometimes ending in a flourish we call innovation. No one planned it, yet the sum looks like choreography. On our last day in the field, we revisit the quarry. Clouds stack up like cards, and the light turns silver. Maya has not heard back about overtime, and the uncertainty sits on her shoulders. She asks if the arms race ever slows down. I say that some ecosystems settle into slower exchanges when energy is scarce or predators thin out, and some speed up when new corridors open, like after a glacier retreats or a canal joins to seas. She nods and says that knowing it changes is enough. Lynn shows a plot where she simulated a dim twilight ocean. The same eye that excelled at noon struggles now, and she writes next to it, "No design wins everywhere." That small sentence feels like a gift. We split one more slab. The rock resists, then yields a ribbon of fine lines that turn out to be a set of gills nested like fans. Even in stone, the breath of that animal feels delicate. While cleaning the fossil, I think of habitats we do not often praise: the thin film where water meets mud, the dark just under the surface, the crowded boundary under a shell edge. The Cambrian Explosion did not only make headlines in open water, it rewired the backstage. Burrowing grew deeper, tunnels crosscut, and the once stable microbial carpet was kneaded into a new texture. In that kneading lies a memory of many small choices that break patterns gently, but steadily. The journalist in my head wants a single cause. The scientist in my head says, take the chorus. Oxygen rises, genes shift, eyes resolve, muscles coordinate, minerals harden, behaviors adapt, and the feedback sprayed. If you take anything from our time together, let it be this: escalation is a teacher, not a villain. Predators and prey co-author complexity. And we, latecomers with cameras and code, arrive with the privilege to notice, to test, and to tell the story in a way that keeps its wonder intact. Support your local museum. Ask your library to host a fossil night. If you ever travel to mountain parks near the Burgess Shale or visit exhibits inspired by Xinjiang and Sirius Passet, go with slow eyes. Let the slabs be more than labels. Look for the tiny hooks on a limb, the faint furrow of a burrow turning back, the healed crack on a plate, and remember that each trace is a solved problem recorded in stone. On the ride home, our team is quiet, the truck hums, and the sky finally opens in a cool rain that drums a patient beat. Maya texts that her overtime was approved for another month. Theo emails a sketch where the ocean is lit not by menace, but by attention. Lynn sends a final note. She reran the simulation with a slower frame rate, as if the brain were a little tired, and the hunter missed more. No design wins everywhere. We laugh because the lesson is as human as it is Cambrian. The first arms race underwater did not crown heroes. It carved habits we still carry. Notice sooner, decide cleaner, and leave room for repair. That is how eyes, speed, and shells changed everything, and why a slab of shale in a quiet lab can still make a room full of strangers breathe in at the same time. Thank you for exploring deep time with me today. Well,